right from where we left off. On screen now, we have an S curve which we've attempted to fit as best as we could through the points which are represented in 2 dimensions. On the x-axis, we have a continuous variable, the number of hours of study. On the y-axis, we have a categorical variable denoting whether the student passed or failed in a test. Let's now turn our attention to some of the math behind this model and how it can be generalized. Just to be clear, the logistic model can be generalized to more than one x variable. We've had one example in which we had a single x variable and we had a predicted categorical variable, but we can generalize this to multiple independent variables, that is, to multiple predictors, pretty easily. Let's keep that context in mind, but for now we'll continue to focus on the simplest case where we have just a single predictor. Such a binary prediction model is going to output a single output number p. This number p is the probability that y is equal to 1. And from this we can easily infer 1 minus p, which is the probability that y is going to be equal to 0. Next, let's turn our attention to the functional form of the logistic regression model. Here it is on screen now. If you look closely at the right hand side of this equation, you can see the similarity with linear regression. This is our familiar functional form theta 0 plus theta 1 x1. However, what's on the left hand side of the equal to sign is not quite so familiar. Here we have the log to the base b could be any number which can be used as the base for a system of logarithms. Of course, the most common choice of b is going to be e, which is the base of the natural log system. The universal constant e is equal to 2.71828. But you should be aware that the logistic function allows us to make use of any legitimate base b. It need not always be e. And this is the logarithm of p divided by 1 minus p. And p divided by 1 minus p really just gives us the odds of the event y equal to 1. The term odds is often used colloquially in common language. However, in probability, it has a specific meaning. In everyday speech, when we use the term odds, we are just referring to any measure of likelihood of a particular outcome. However, in terms of probability, the odds measure the ratio of the probabilities of that event occurring to the probability of that event not occurring. In the world of discrete probabilities, this is the same as the ratio of the number of events that